Hey guys, good morning. So we're going to be looking at the Coulombic attraction as well as just the Coulombic attraction worksheet for right now, and then we'll get to the other stuff after this. Okay. So I got a couple things ready here in my little whiteboard thing here. Why is it not working like that? Okay, that works just fine. I guess because I have my mouse plugged in. Okay, anyway. Sorry, I'm mumbling to myself. It's early in the morning. All right, so we're going to be looking at Coulombic attraction today, and Coulombic attraction is the basic principle behind pretty much all the periodic trends, and it helps if you understand Coulombic attraction, then you can more easily understand the periodic trends. Periodic trends are important in understanding how elements and atoms react with one another. Okay, Coulombic attraction is the attraction between oppositely charged particles. Okay, for example, when we talk about the atom, we're talking really about protons and electrons, right? Protons are positively charged, electrons are negatively charged. Okay, so let's look. The first factor that comes into play when we talk about force of attraction is the distance, right? So number one, first, let's define what these particles are. This positive particle is a proton, and this negative particle is an electron. Pretty simple, right? Proton, electron. Okay. Would you observe the attraction or repulsion? We would observe attraction. Obviously, protons and neutrons attract one another. Okay. Now we look, what are the independent and dependent variables? Independent is what we determine, so what we determine, and then dependent is the result of that. So what we're determining here is the distance. We're changing the distance, and then based on the distance, the dependent variable is the force of attraction. We can often tell that because, look, the change in distance is consistent. This is always 0.1 nanometers. It's always increasing by 0.1, whereas the force of attraction is changing a little bit differently each time. Typically, if we're changing something, we want to change it at a consistent rate. So that's how we know it's the independent variable. Okay. My cat is making this really hard. He's right here. He doesn't like me working. Okay, write a complete sentence that describes the observed relationship between independent and dependent variable. As distance increases, force of attraction decreases. Okay, if the distance between proton and electron is 0.5 nanometers, so it's longer than the last one here, so the last one's 0.3, would you expect it to be greater than or less than? So as you see, it's going down, so it would be less. So the force of attraction decreases over time, or over distance, I should say. If two protons, so if we added two protons, are 0.1 nanometers away from one electron, would you expect the force of attraction to be greater than or less than 2.3 nanometers? So we look back at the first one here. Right now, there's one proton, and the force is this. You're not actually expected to really know this. This is a guess. So what would you guess? So it doesn't matter if you got this right or wrong because it's a guess. However, if we do increase the number of protons, we increase the attraction. Okay, and that's actually going to play into the next part. Okay, not right now, but very soon. Okay, now we're looking at this in action. So we're looking at distance and force of attraction in action in the periodic table here. Okay, so here we have the alkali metals. So these are all in the same group. Okay, these arrows are representing force of attraction. Okay. How does the thickness of the arrow apply or relate to the property given in part A? Thicker arrows equal stronger attraction. Okay. Using a periodic table, locate the elements whose atoms are diagrammed, and are they in the same element or the same row? Sorry, are they in the same column or same row? Element, column. They are in the same column. They're all part of the alkali metals. We can even look at the periodic table. I brought it up here. So you have lithium, sodium, potassium, all right there in the same column. Okay, they're all the alkali metals, or they're all alkali metals, I should say. Okay, as you go from the smallest atom to the largest, how does the distance change? It gets larger distance. Okay, and as you move from the smallest to the largest, how does the attractive forces change? They get less attractive. Just like as I get older, I get less attractive. Just kidding. So as the atom gets bigger, the force of attraction between the protons and electrons gets weaker because the distance gets greater and greater. And is that consistent with Model 1? Yes, of course it is. It's consistent with the rules of Coulombic attraction. Okay. Now, why is the distance getting greater? That's one question I didn't ask. The reason is because we're adding energy levels. If you recall, Niels Bohr said that atoms have electrons that are in specific energy levels. Okay? As you move down the periodic table, you're increasing the number of energy levels. Everything in the first period has 1, then the second is 2, then 3, then 4, then 5, and so on and so forth. Okay, so as you go down the periods, or as you go down the columns, I should say, and you increase the period number, you're increasing the number of energy levels. So you can think of it like a Russian nesting doll. So you have, or even like an onion, they have layers. Okay, as you add more layers, more energy levels, it's getting farther and farther away from the nucleus. Okay, that's important, really, really important to understand that as we go down, we add energy levels. As we move from left to right, we don't add energy levels. We're just adding protons and electrons. Okay, so really make sure you understand that. Move down, we're adding energy levels. That's really, really important. Okay? Okay, next part here. Okay, Jack's biting my hand. Stop it. Okay. Number of protons and attractive forces. So now we're going to be looking at basically what happens as we move from left to right on the periodic table. Okay. So here, what are the independent and dependent variables? Independent is the number of protons. Oop, I hit the button. Number of protons. Okay. The dependent is again the force of attraction. Okay. And what is the relationship between these two things? Well, the relationship is as number of protons goes up. Oops. Bear with me here. As the number of protons increases, the force increases. Okay, protons go up, force increases. Okay, what should be the attractive force on a single electron if 5 protons were in the nucleus? Okay, if you look here closely, every time you move up, you're adding 2.3 times 10 to the negative 8th. Then here you're adding 2.3 times 10 to the negative 8th. Same thing. So if we were to add another proton, we'd be adding 2.3 times 10 to the negative 8. So add 9.2 plus 2.3, you get 11.5 times 10 to the negative 8. Or more accurately, it's 1.15 times 10 to the negative 7. Okay, because that is correct scientific notation. Okay. Now imagine a second electron were placed to the left of a nucleus containing 2 protons. So 2 protons, 1, 2. We have an electron over here, an electron over here. They're the same distance. They're 0.1 nanometers. Would they have the same amount of attractive force? That's the question. Okay. Now you don't know this. This is a guess. They like to do this. They like to ask you to guess. So go ahead and guess. I'm going to tell you that the attractive force should be the same as if there was only one electron. So it should be 4.6 times 10 to the negative 8 and 4.6 times 10 to the negative 8. Okay, it's the same. The reason for that is these protons are acting together. These electrons are not acting together. They are acting individually. Okay, electrons do not, their attractive force is not additive. The proton's force, however, is. The reason that the proton's force is actually because in the nucleus we don't just have protons, so protons typically would repel each other. However, we have neutrons as well. And neutrons are like glue. Okay, they hold protons together and they make them act as a single unit. Okay, so in something like helium always has at least two neutrons. Okay, to hold those protons together. Without neutrons, protons cannot stick together. Okay, and they do not act the same, but they do not act together. But because there's neutrons, they do act together. Okay, so this next part here is demonstrating this. So as you said, the two protons would have the same pull on the electrons, regardless of how many electrons there were. Okay, so if we had 3 protons, so here we have 3 protons. Okay, would that change the attractive force in electrons? No, not substantially. Not substantially. Okay, well, I should say the 3 electrons wouldn't change the force that 3 protons have. Okay, 3 protons would still have 6.9 times 10 to the negative 8 for all 3 electrons. Newtons of force. Okay. So when number of protons increase, the attractive force also increases. Okay. Doesn't matter how many electrons there are, the protons will always increase. Okay, next. So let's see this in action. We have sodium, aluminum, and chlorine. Okay. So using periodic table, locate the elements who are diagrammed here. Okay. So if we look at the periodic table, oh, it's so far away. We're looking at sodium, which is here. And then we have aluminum. And we have, what was the last one? Chlorine, I think. Yeah, chlorine. They are all in the same row. Okay? They're all in the same row on the periodic table. So as I said before, if they're in the same row, they're not adding energy levels, and that's indicated by the drawing here, right? They're not adding energy levels. They have the same number of energy levels. The only thing they're changing is the number of protons and number of electrons. Okay, so in the same row. Okay, circle the outermost electrons. I think I just asked you to tell me how many are in each there. I changed this question around so you can just type it. Sodium has 1. outer electron, aluminum has 3 outer electrons, and chlorine has 7 outer electrons. So 1, 3, 7 electrons. Now, which one of these has the strongest attraction? It's actually chlorine. Okay? So what's happening is we're not changing the distance, but we are adding we're adding protons. Okay, so does the distance change? No, not significantly. Okay, when we talk about distance, really what we're going to be talking about, energy levels. Okay, energy levels. Now, can the attractive forces be shown by the arrows be explained by a change in distance? No. So it must be, if it's not distance, it must be number of protons. Okay, if we look at the number of protons, okay, look at the number of protons. Sodium has 11, aluminum has 13, and chlorine has 17. So 11, 13, and 17. Move it over here, make this easier. So 11 for sodium, 13 for aluminum, and 17 for chlorine. Okay. So can the force of attraction be explained by the change in number of protons? Yes. More protons equals more attraction. Just like more money means more attraction, right? Right, ladies? Right, men? Right, like guys? Get those sugar mamas and sugar daddies, right? Okay, now let's look. For each set of elements below, circle the element whose atoms have the strongest attractive forces. Okay, so let's look. Barium and calcium first. Zoom out here. Making this harder on myself here. Let's find where barium and calcium are. So barium and calcium are in the same column, if you see here. Barium is lower than calcium. Now, as I said before, as you go down in a column, we're adding energy levels. So the distance is increasing. Okay? So the distance between the protons and electrons in barium will be greater than that of calcium. So since barium has more energy levels, the electrons are further away, calcium will have the stronger attractive forces. So calcium has stronger attractive forces. And erase some of this stuff here. Next one, chromium and copper. So chromium's here and copper's here. They're in the same row. So this time we're looking at number of protons because we're not changing the energy levels, we're not changing the distance, we're looking at number of protons. Okay, the one with more protons will have the stronger attraction. So copper has more protons, therefore it will have the stronger attraction. Next one, argon and xenon. So argon and xenon are both noble gases. Argon's here, xenon's here. These are in the same column. So this one we're looking at energy levels and distance. Okay, the more energy levels, the weaker the attraction. Okay, so xenon has more energy levels, therefore it has weaker attraction. So argon will have the greater attraction. Oh, I just dropped my pen. So argon has the greater attraction. Wonderful. Wonderful, wonderful, wonderful. Okay. Should be one more part of this worksheet here. Yeah, there it is. Okay. On each diagram, write the number of protons in the nucleus of the atom. So let's look at model 2. Let's go back and look at model 2. Okay, and what we're going to be looking at is number 1, the number of protons in each atom, and then comparing the elements in the same column, which factor distance to the nucleus or number of protons seem to be a dominant factor. Okay, and explain. So let's go back to it. Let's look at model 2 again. Plus big mess. So if we look here, lithium has 3 protons. Okay. Sodium, I believe, has 11 protons. And then I forget how many potassium has. I want to say 19, but I could be wrong. Let's look at it real quick. Oh, I'm right. Potassium has 19. I'm so smart. No, that's just what happens when you teach chemistry for a long time. You start to memorize these things. Okay, so we're actually increasing the number of protons. So what the heck? Why are we changing? Why? Oh my God, this is so confusing. Why is it less? Why is there less attraction? Oh wait, I know. It's because we're increasing the distance. Distance matters more than protons. Okay, so the distance between the protons and electrons, that matters more than number of protons. Okay, so as we move down the period, the distance is a bigger factor than the number of protons we're adding. Okay, it's really that simple. It's really that simple. But that's important to know. So distance matters more. Distance. Oops. Distance matters more. Okay. And let's just not even worry about these. Don't even worry about those ones. Done. Let's call it a day. Let's not make it any more confusing. So there's 2 factors, distance, number of protons. Distance matters more. Distance comes into play when we talk about up and down on the periodic table in a column. Okay? As we move from left to right, the number of protons matters. So as we add protons, we increase the attractive forces. Okay, that's Coulombic attraction. That's it. We're going to use those things. We're going to use those to eventually explain the periodic trends, which is in the next video. So stay tuned for the next video.